All right, next up what we want to talk about is the identity matrix. An identity matrix is a square matrix, all of whose main diagonal entries are ones, and all of its other entries are zeros. So here's a few examples of identity matrices. They have to be square and they have to fit that criteria. Now, identity matrices are really, really important in the discussion of matrices, and so we give them their own symbol. An identity matrix is always notated by a capital I. If we want to mention the dimensions of an identity matrix, for example, this is a 4 by 4 matrix, I could call this I4, indicating that common dimension 4 by 4, or for an n by n matrix, IN. But more often than not, we're just going to use I because oftentimes we don't need to include the dimensions in this discussion here. It's usually clear from context what the dimensions of that matrix would be. So the purpose of the identity matrix is that it's a multiplicative identity. What that means is it acts like the real number 1 when it comes to multiplication. If I take any real number, x, let's say, and multiply it by 1, either if I do 1 times x or x times 1 in either order, I get x. So in other words, multiplying by 1 doesn't change the number I multiplied it to. The identity matrix does the same thing. And you can verify this on your own just by, working through a couple of examples. But if I pick any matrix A, for example, and multiply it on the left by the appropriately sized identity matrix. Remember, the dimensions have to correspond to each other in that particular way. In other words, I has to have the same number of columns as A has rows, but if you have the correct dimensions here, I times A will always be A. Similarly, if you multiply on the right by the appropriately sized identity matrix, for any matrix B where this is defined, B times A will equal B. Again, I'm not going to prove that for you. I'm just going to let you look at that on your own. It's very easy to see once you've worked through an example or two why the identity matrix does this. So again, we call that that's multiplicative identity, and it's very similar to the number 1 for real numbers. An important fact about identity matrices also is that they're equal to their own transpose. I had hinted at this before. Matrices that are equal to their own transpose are called symmetric matrices, and we'll talk about those in section 1.7. But this is an important property that we're going to use in a proof or two, the fact that the identity matrix is equal to its own transpose. See if you can see why that's the case here. All right. So having introduced that, we can now talk about this theorem. So if R is the reduced row echelon form of an n by n matrix A, then either R has a row of zeros or R is the identity matrix. It has to be one case or the other. And it's important to note that we're only talking about square matrices here. N by n matrices would be square. Okay, so the proof is this proof is straight out of your book. We're just going to go over this really quickly. Suppose that you have a matrix A, it's an n by n matrix, and its reduced row echelon form is this. Okay, now either the last row in the matrix will consist entirely of zeros or it won't. If it does consist entirely of zeros, then there's nothing to prove here because, again, the statement of this theorem says that if we're looking at our reduced row echelon form, this guy right here, then we either have a row of zeros or the entire thing is the identity matrix. So if there was a row of zeros, we're done, nothing to prove. So let's assume that it does not have a row of zeros. Now, because we're talking about the reduced row echelon form, and because we have the same number of columns as rows in a square matrix like this, then every row and every column will have to have a leading 1 in it. Now think about why that's the case. If we didn't have a leading 1 in each of these rows, then that would imply that we skipped a column. But then we would have less than n leading 1s in this entire matrix. That would mean that as we kind of move from left to right, finding these leading 1s, we would reach the end, the very last column, before we reach the last row, forcing that bottom row to be a row of zeros, because that's what the reduced row echelon form would include. So what that means is essentially the leading ones are going to have to follow this pattern where we have one in the 1-1 position, and then the next would have to be in the 2-2 position, and so on and so forth. And that's going to create an identity matrix, leading ones along the main diagonal, and then because it's reduced row echelon form, zeros everywhere else. So that's kind of talking through somewhat informally that proof, but here's a description of that, and you can read through that. It's essentially just saying the same thing we just discussed. Let's go ahead and move on, though. All right, here we are. Okay, so now on to the discussion of invertible matrices. So if A is a square matrix, and if there exists a matrix B such that A times B and B times A are both equal to I, then we say that B is an inverse of A. Now, this is interesting because, again, remember, in general, multiplication with matrices is not commutative. Normally, A times B is not equal to B times A, but you may remember I said there are some cases where that does happen. It just does not happen in general. In the case of a matrix and its inverse, if such an inverse exists, those two will commute, and in either order, their product will equal an identity matrix. So not every matrix has an inverse. First of all, in order for it to have an inverse at all, it has to be a square matrix. But even some square matrices, a lot of square matrices, in fact, do not have inverses. We're going to show an example where that's the case in a moment. We single out the matrices that do have an inverse, and we call them invertible. Another term for that is non-singular. We're going to use this term more, but just know that these are synonyms. If no such matrix B exists that gives us this property, in other words, if there's no matrix that I can multiply on the right and on the left by this matrix A to get the identity matrix, then A is said to be singular, and which would mean it's not invertible. So let's do an example where we verify that two matrices are, we have a matrix A and this matrix B is its inverse, or an inverse. Okay, so all this really requires us to do is to form the two products AB and BA and check that each product gives us an identity matrix. So what is AB? That's 1, 2, 2, 3 times -3, 2, 2, -1. Okay, so forming this product, we should end up with a 2 by 2 matrix. I'm going to have -3 times 1 plus 2 times 2. That's -3 plus 4. That's 1. Okay, let's go down to this entry down here. So this column times this second row. -3 times 2 is 6. 2 times, is -6. 2 times 3 is +6. -6 and +6. That's going to add up to 0. And then let's do our 1, 2 entry. So second column, first row, that's 2 times 1 plus -1 times 2. It's 2 plus -2, which is 0. And then finally down here, 2 times 2 is 4. -1 times 3 is -3. 4 plus -3, that's 1. And that's an identity matrix because its main diagonal entries are 1s, and every other entry is a 0. If you reverse the order of this, so -3, 2, 2, -1, times 1, 2, 2, 3. I'm going to let you check this. You verify the arithmetic works out. We also end up with the identity matrix in this case. Okay, so that would show that B is an inverse of A. All right. Now, one other thing that's worth pointing out here, if B is an inverse of A, then A is simultaneously an inverse of B. Because if B is the matrix that we're calling A up here, if we reverse their roles, then the same property shows that the product of those two gives me the identity matrix in both cases. So if A is an inverse of B, then B is an inverse of A. They have that relationship. All right, now here's a 3 by 3 matrix. And we want to show that A is singular. So remember what this means. In order to show that A is singular, what we need to do is show that no matter what matrix I try to multiply A by, I will never ever get the I'll never ever get the identity matrix from that. And here's how I can show that. I can't multiply by every 3 by 3 matrix in existence because there's an infinite number of those. So there's no possible way to actually check for every matrix that I can choose B. That'll never happen. So we have to think in more general terms. Let's suppose for a moment that I take this matrix B and I multiply it by our matrix A. And again, A is going to be assumed to be a 3 by 3 matrix because if I have any hope of doing this multiplication in both orders, BA or AB, then it would have to have the exact same dimensions as A. Now, what I'm going to do, rather than do my multiplication directly, I'm going to use a property of matrix multiplication that we've talked about back in section 1.3. I'm going to take these columns here and name them. So I'm going to say this column, let's call it C1. And notice this column right here, I could call it C2, but there's something worth noting about this. It's a zero vector. It's a matrix containing only zeros. So I'm going to notate that actually by 0. Remember, 0 is our notation for a zero matrix. And because I can't make my 0 bold when writing it in pen, I use this little arrow notation instead. But that's still saying that this is a 0 column. And then this column is not a 0 column. I'm just going to call it C3. Okay? I suppose I could actually be using arrow notations for these as well. So let's go ahead and do that. Okay, so what I'm doing is I'm naming my columns so that I can write A as a partitioned matrix. This is B times C1 times a column of zeros times C3. Now, if you remember, we showed in section 1.3 that if you write this matrix in partitioned by its columns like this, then you get something that resembles a distributive property. This is B, C1, B times the 0 vector, B, C3. Okay. However, we also showed in section 1. Actually, no, we showed it in this section when we introduced the 0 matrix, that any matrix times a 0 matrix is a 0 matrix. So this is equal to B, C1 times, and then my second column is going to be the 3 by 1 0 matrix, and then this is going to still be B, C3. Now that's actually enough for me to say that this is not equal to an identity matrix. And why is that? Well, if this were equal to an identity matrix, every column in an identity matrix should have a 1 in it, whichever entry falls on the main diagonal. But this, my second column, is going to consist of all zeros. There's no 1 in this column. So that means regardless of what the matrix B was, there's no way that this multiplication could ever churn out an identity matrix. Okay, if you wanted to prove this in a more direct way, then what you could do is set B equal to some arbitrary 3 by 3 matrix. You could name the entries, A, B, C, D, E, F, G, H, I, or something like that, and then do the multiplication directly and show that that middle column would still be all zeros in that process. But this is more compact notation. We get there faster using this property. Okay, so important example because, again, it shows that not every matrix, not every square matrix has an inverse. So a big, big question in this course, and we start answering this question in chapter 1, and then we continue working on this throughout the book, is how to develop criteria to determine whether or not a matrix is invertible. And it turns out the statement that a matrix is invertible is equivalent to a number of other really, really important and useful statements, giving us a really interesting characterization of invertible matrices versus singular matrices. But that's kind of a bigger topic that we're going to continue working on. It also says in this example, does this generalize? Well, notice there was nothing really special about this particular matrix here other than it had a column of zeros. The fact that there was a column of zeros here is what led to this result. The fact that multiplying on the left by some other matrix will always preserve that column of zeros. So if we're looking for a generalization of this, it would seem logical that we could say any matrix, any square matrix with a column of zeros anywhere in that matrix could not be invertible, because a similar result is going to occur. In fact, you could even go further and say a matrix with a row of zeros will also not be invertible. We're going to show, using other techniques later, why that would also be the case, but we can actually prove both of those right now. But let's go ahead and move on. So now let's talk about a really important theorem concerning invertible matrices, which is to say that if B and C are both inverses of a matrix, then B is equal to C. This is called a uniqueness theorem. And what it says is that if the matrix A is invertible, then it has one and only one inverse, or the inverse of that matrix is unique. It cannot have several different inverses. And we oftentimes state uniqueness theorems by saying, let's suppose that there's two of these entities or two of these objects, then that would imply that they're in fact the same object. The proof of this just uses the properties of matrices that we've already talked about, namely the associative property. So let's suppose A is a square matrix, and let's suppose that B and C are also inverses of A. The goal is to show that B is equal to C. So I start with B here, and my hope is to establish a chain of equalities here, ultimately getting to C. This would establish that B is equal to C. So B is equal to BI because, again, remember, multiplying by an identity matrix is like multiplying a real number by 1. It's supposed to give me B in this case. Now, the identity matrix is also the same thing as AC. And this comes from the assumption that C is an inverse of A. Remember, A times C in either order, so AC or CA, should result in the identity matrix. So this just follows from our assumption. Now I can use my associative property of multiplication to regroup the BA as the first product I want to do. And here's where I would again use my assumption. Remember, B is also an inverse of A. So B times A should result in the identity matrix. So now we have IC, but again, because I is an identity, IC will equal C. So B is equal to C, showing that if you have any pair of inverses of a matrix, then you're actually talking about the same inverse. Therefore, the inverse of an invertible matrix is unique. Now, because it's unique, instead of saying B is an inverse of A, we can now say B is the inverse of A. And with that, we can also justify using a special notation. If A is invertible, then we're actually going to notate its inverse as A to the negative 1 power. The reason for this notation is because the inverse of a matrix functions in a similar way as the reciprocal of a real number. If you think about it, if you take a non-zero real number and you multiply by its reciprocal, you get the number 1, which is the multiplicative identity for the real numbers. In the same fashion here, the matrix A, when multiplied to its inverse, if it exists, A inverse, should give us I, the identity matrix. Okay, so that's why we borrow this notation, A to the negative 1 power, which would normally be like the reciprocal if this were a real number. That's not literally what that means. That negative 1 does not mean that we're taking a literal reciprocal of a matrix, because there is no such operation. But that's the notation that we're going to use. Okay. So now a logical question arises here, which is, if I have a matrix A and it happens to be invertible, how then can I determine what its inverse looks like? We did an example just a little while ago that showed that a given pair of matrices were inverses. But let me come back to that one actually. Let's suppose that in this example here, I didn't give you both of these. What if I just said, hey, A is this matrix right here. Let's assume it's invertible. Find its inverse. That would mean that you have to find this matrix somehow. How would you come up with this? Well, in the case of a 2 by 2 matrix, we have an algorithm for doing that. Now, I'm not going to derive this algorithm like deductively. We're not going to show where this comes from. We do have the tools to do that here, but we're actually going to come up with a much more powerful algorithm in the next section that sort of replaces this. I have to emphasize this really strongly. This algorithm only works for 2x2 matrices. Don't try to apply this to any other square matrix. Okay, in order to accomplish this, we need to introduce an important function that we apply to square matrices called the determinant. We're only going to define the determinant for 2x2 matrices here, and then in chapter 2, where we focus very heavily on the determinant, we'll generalize this to any square matrix. But for a square matrix, 2x2 square matrix A, where the entries are A, B, C, D like this, the determinant is defined to be AD minus BC. In other words, it's the product of the main diagonal entries minus the product of the other diagonal entries. With that definition, we also denote this determinant as det, or det with an A in parentheses here. Please note that the determinant takes a matrix, a square matrix, as an input, but its output is not another matrix. It's a real number or a scalar. Okay. It's gonna take a lot of work, but we'll eventually develop some intuition as to what the determinant actually represents, geometrically even, and that's going to take us until the end of chapter 3 to actually get that idea down. But anyways, we need the determinant for our algorithm for finding an inverse matrix. So if matrix A is this 2x2 matrix, A, B, C, D, it turns out that it's invertible if and only if the determinant of A is not equal to 0. And then if this is the case, this is what our inverse is equal to. So it's 1 over the determinant of A. Remember, that's a scalar, so this is the reciprocal of that scalar, times the matrix that that swaps the main diagonal entries. So instead of AD, it looks like DA, and then keeps the other diagonal entries where they are, but takes their opposites. So negative B here, negative C. So it's scalar multiplication on this new matrix. Okay? We are not going to prove this theorem because we're going to prove a much more powerful version of this in chapter 2, which is to show that if you have any square matrix, if the determinant of that matrix is not equal to 0, then it has an inverse. But we don't have the tools to do that yet. So this will end up being a special case of that more general proof later. And then if you want to prove that this is the inverse of this, what you can do is just multiply A times A inverse and use your homogeneity property to bring the scalar all the way out. Homogeneity is one of the properties of matrix multiplication that we went over in section 1.3. Carry out the multiplication and show that the result is an identity matrix. It's a straightforward exercise, so we're not going to do that here. I want to show that the matrix A, 2, 3, 2, 5, is invertible, and then I want to find the inverse of this matrix. So the first thing is to show that the determinant of this matrix is non-zero, according to that theorem we just talked about. And the determinant of A, which, by the way, another notation for that is this, 2, 3, 2, 5. If you notice, I rewrote the matrix, but the square brackets became straight vertical lines. This is another way of saying the determinant of that matrix. It's the product of the main diagonal entries, 2 times 5, minus the product of the other diagonal, which would be 3 times 2. That's equal to 10 minus 6, or 4. That's not equal to 0, and so we have an invertible matrix. The next step is to compute that inverse. So A inverse is equal to the reciprocal of our determinant, which would be 1/4, times, and now remember, I take the main diagonal entries and I swap them. So it becomes 5, 2. And then I take the opposite of the other diagonal, -3, -2. If I want, I can go ahead and leave my answer in this form. Or if I want to perform the scalar multiplication, I can also multiply everything by 1/4. So that becomes 5/4, -3/4, -1/2, +1/2 right here. Okay? That's going to be it for this video. We'll move on to the next theorem in the next video.